Hi everyone, I am Chufan Lai from Peking University. I will introduce our paper entitled Automatic Annotation Synchronizing with Textual Description for Visualization. People have all sorts of findings in data analysis. To share these findings, a visual presentation would be a good choice. That is, explain the insights while presenting the data with visualization. To understand the presentation, the audience needs to match what they hear and what they see. We call this process text-visual matching. It is not as easy as it seems. Let me explain with a small example. Now, this is a dimension-reduced projection. It depicts the traffic behaviors of over 18,000 vehicles in a national park. I will present our findings in several ways. First, let's pause for a moment to read. Can you find everything mentioned in the text? I guess it takes time, right? What if we add some annotations? Try to go through the description this time. Now, how about some animations? It's much easier to follow the presentation, isn't it? So, from the audience perspective, animations are better than images, and annotations are better than pure text. That's because in the process of matching, people have to switch their attention frequently. Annotations help to highlight the targets and bind text to image areas. Animations help to separate multiple targets so that we can focus on one thing at a time. However, all benefits come with a cost. It's easy to type in the text, but making animations can be a mission impossible for inexperienced users. What we aim to achieve is to make it a piece of cake to everyone. More specifically, given a visualization with its description, we aim to automatically generate a series of annotated animations for a vivid presentation. We propose a three-stage workflow. First, we figure out what is in the visualization. Then, we try to understand what the text describes. And last, we match these two to understand which entities in the image have been described by which sentence. It allows us to annotate correctly and generate the animations. Based on the workflow, we implement a prototype system called VisAnnotator. It contains three modules: object detection, natural language processing, and annotation. I'll introduce them one by one. The object detection module is designed to teach a computer to read a visualization. More specifically, it identifies all entities in the chart that can be visually perceived, which we call visual entities. There are two types of visual entities. Data entities refer to geometries that encode the actual data, like the bars in a bar chart or the points in a scatter plot. Their contours are needed for highlighting. Auxiliary entities are those used to convey contextual information such as axes, color legends, titles, etc. We need the information they contain, but not their contours. There do exist classic methods to extract visual entities. However, they are mostly designed for a certain type of entities. It requires a mix of them for comprehensive detection. Besides, it's hard to apply them to new visualization types. Seeking to build a more concise and extendable framework, we adopt object detection techniques. Object detection is a class of deep learning models in computer vision. It can identify both the type and the location of each object in the image. Based on that, instance segmentation models can find out the exact image areas and output the contours. We use Mars-RCNN, a state-of-the-art instance segmentation model. An implementation of it is provided by Textual, an open-source deep learning library. Mars-RCNN is widely used in computer vision, but never applied to visualizations. Theoretically, it will work as long as the target has stable visual features. To build our own model, we first collect a visualization image corpus from the internet. Then we label all visual entities in each image. After training, the model can output both the bounding box and the contour of each entity. However, for data entities, the original contours are too rough due to subtle deviations in the prediction. You can see the irregular boundaries in this example. So, we add an extra step to refine the original contours by outlining the image area containing the entity's major color. With the contour, we extract other information like color, size, location, etc. For an auxiliary entity, we extract information from its image area by applying optical character recognition and image processing techniques. The extracted textual information is passed to the NLP module to help interpret the description. The current model is trained using bar charts, pie charts, and scatter plots. We get about 90% prediction accuracy on the test set, meaning that Mars-RCNN can be successfully applied to visualizations. Other chart types can be supported as long as their samples are added to the training set. Okay, now we come to the second module, natural language processing. This module teaches the computer to interpret a description. First, let's talk about how we describe what we see. There are three ways in general. You can call its name if you happen to know it. If you don't know the name, you can describe its visual properties. Or you can describe its relationship to another known entity. Accordingly, there are three ways to envision what we hear about. Use its ID, type, its visual properties, or its spatial relationships. Our brains will generate search conditions to help find the entity from sight. That leads us to the task of the NLP module, namely to extract entities mentioned in the description, as well as their IDs, types, properties, and relationships. We first apply basic NLP techniques including text segmentation, POS tagging, and dependency parsing. However, a word's part of speech doesn't tell about its type or role in visualization. The dependency tree cannot handle different types of expressions. We use keyword matching to detect the types of words. Specifically, we build a keyword library that contains a common vocabulary for visual descriptions. Auxiliary information from the object detection module is used to identify chart-specific words. We also build a structure library to handle different dependencies in equivalent expressions. The key structure shows the decorating relationship between keywords. The above procedures turn the text into a structured list of described entities, which is passed to the annotation module as search conditions. The NLP module can handle various keywords and expressions as long as they are included in the predefined knowledge bases. The annotation module has two tasks. One is to match results obtained from the previous modules in order to find the visual entities mentioned in each sentence. After that, it annotates the chart with each sentence and generates animations for presentation. The matching is done by cross-filtering visual entities using NLP-generated conditions. Given the contours, we highlight entities using image masking. The whole sentence is displayed near its target as the annotation. Different sentences are shown in the original order. This demo shows how our system actually works. You can see how the user uploads materials and get a series of animations. In order to evaluate the performance of our system, we need to assess both the rendering and the accuracy of the annotations. It's also important to improve accuracy by finding out the causes behind inaccurate cases. First, we conduct a user study involving 10 participants, all of whom are graduate students with computer science backgrounds. After the introduction and training, each participant is required to provide 2 visualization images. It leads to a task corpus with 20 different charts. Then the participants help assess the rendering of the correct use case. At last, they pick out random samples from the corpus to test the accuracy of our system. In the third step, participants are asked to read a given chart with its description, upload it to the system, and grade the annotations considering 5 different aspects. Results show that the highlighting, overlays, and animations are doing well, while there is still space for improvement concerning the inclusion of annotations and text readability. In the fourth step, each participant is asked to randomly pick out 12 images from the corpus. For each image, the participant needs to write a 1-sentence description for testing. Results are considered correct if and only if all mentioned entities are identified without any mistake, omission, or redundancy. The overall accuracy is about 60% for the 112 use cases. We go through all inaccurate cases to find out the causes. It turns out most failures are caused by NLP errors, especially the grammar mistakes made by non-native English speakers. Some others are due to OCR errors, while the object detection works fine. Now, let's take a closer look at some use cases. Here, we display 6 correct cases in 3 different charts. They demonstrate the ability of our system to handle different types of visualizations, multiple focuses, as well as different expression styles. These are 2 incorrect cases. In the first case, the user tries to describe the rightmost group of bars, but nothing is highlighted. That's because the sentence structure he uses is not included in our knowledge base. In the second case, the user also tries to describe the rightmost group, but only 1 rectangular is highlighted. That's because the name I just did in the current legend is wrongly identified, leading to a failure in the NLP module. So, to sum up, our system is proved effective with about 60% accuracy. It can be further improved by more robust OCR and language models, as well as more complete NLP knowledge bases. Allowing manual correction also helps. We also need better annotation layouts and more prominent texts. In the future, we plan to extend our work to real-time speech-based annotation. We will also try more complex visualizations and even natural images. Finally, I would like to thank my colleagues as well as funding projects and agencies. Thank you.